Thank you all. And today we're going to dive deep into SHAP and explore how we can move beyond just treating our ML models as black boxes. Now, if you attended the previous talk, I think from Yashi, so then you probably know why XAI is so important. Chances are you're probably been in that room where there's an uncomfortable question saying that why did the model decide it that way? So with this talk, hopefully you'll be able to have some tools to answer those questions. So a little bit about me. So I'm based in California, in the Bay Area, in Sunnyvale. I am running on caffeine right now. I have just woken up probably, right? So I'm a staff data scientist at Intuit, where I build models for time series and revenue predictions. I'm also an editor at PyOpenSci, which is a nonprofit for broadening the acceptance of scientific Python packages. And interestingly, I come from both the engineering and the data science background. I have moved back and forth between either of those spaces, but now I'm right there in the middle. I love gaming. I am a huge gaming fan. I love PS5, and I can't believe that I left my Steam Deck at home. Anyway, let's move on. I love football and tennis. I actually wrote soccer, but now since we are in the right place, I say football. And I also love driving. Some certain conditions have to be met. It has to be a lightweight, rear-wheel drive sports car with a stick shift. And this is me in my car in Laguna Seca in California. My next bucket list item is to drive in the Nürburgring. We are not far from there, so hopefully. All right. So the agenda for today is to really talk about why explainability matters. I won't go deep into all of that, but mostly with the theoretic explanation behind SHAP and the mathematical intuition behind SHAP, right? And then we will actually dive into two case studies, which are very relevant. I'm not picking some random case study here. So these are pretty relevant in today's day and world. And then we'll also talk about the limitations, of course. So with that, we have a lot to cover. So I'm just going pretty fast here. So why does it matter, right? The problem is, well, unfortunately or fortunately, whatever so you choose yourself, ML projects is not just about fun projects anymore, okay? It is making decisions that affect people's lives, okay? So it matters, right? So it's used in very critical industries. Resume screening for a job application. So when an AI rejects your job, you deserve to know why. And was it your education, your experience, or is it something else, right? When an AI says that you might have cancer, well, both you and your doctor deserve to understand what the model saw in that image, right? Then for credit risk, so if you're denied a loan and the algorithm just said no, well, that is not good enough, right? Because especially if it's based on some kind of a biased data set, okay? So, and of course, finally, we have the ethical concerns, right? Without explainability, we can't detect bias, ensure fairness, or build any trust, all right? So now we will focus on the Shapley values from where the SHAP originally is derived, okay? And there are different techniques for explainability, as we all know, but one of the most popular ones is SHAP, okay? So the formula is this, right? So it's pretty clear? Or no? Well, you don't have to understand this formula, so let's understand it a little better with a concrete example. So let's imagine we have 3 friends who start a business and bring in about 20K in profit, okay? These are dollars. You can convert it to euro if you want to. Now, Alice alone, if only Alice alone started this business and was working on it, she would bring in 5K in profit, okay? If it was only Bob alone, he would actually bring in 3K in profit. And if it was only Charlie alone, he would bring in 4K in profit, okay? So you can see that individually, they can get only about 12K, okay? So who gets the credit for the rest of the 8K, which these 3 friends actually bring in? Well, that's the magic of collaboration. That's actually a latent property that is not understood by just the face of it. So the whole is greater than some of its parts, right? So maybe Bob brings in some X factor to the business that is not really understood when you are just looking at it from a standalone perspective, okay? Now, Shapley values solve this problem by testing each possible combination. What if only Alice and Bob work together? What if Bob and Charlie teamed up, okay? So we calculate how much each person contributes in every scenario, then average it out, okay? So the origins of this is actually from cooperative game theory, where you have to distribute rewards among different players, okay? But in ML terms, really, what you're looking at is a player equals a feature. A game is an ML task. And an ML task could be like any kind of a task. It could be a classification, regression, recommendation, ranking, you name it, right? And now we move into SHAP. Okay? SHAP is a specific implementation of Shapley values to explain the ML predictions. All right? It is actually modeled as a linear model of feature contribution. So you can think of it. So we'll actually go into the next slide, but it's actually a linear model of all the feature contributions there. Okay? The best part about SHAP is it's model agnostic. So you could have a decision tree, you could have any neural networks, you can have any kind of model. It could be an SVM, logistic regression, you just name it, okay? So the mathematical intuition is pretty important, because once you understand it, you will really understand what SHAP is doing from behind the scenes, okay? So we have this formula. This is, this is not a difficult formula, but it's important to understand what each of these things mean. So f of x is the prediction of a single instance. Now, by a single instance, I mean one single customer. Okay, so if you have your banking data set or your credit analysis data set, so this is one single instance, which is one single customer. All right. Now, E of f, which is the expectation of f, is the mean prediction of the data set, of the data set, or the background prediction, or the background data. Okay, so that is our baseline prediction. Okay. Basically, to answer that question, what would happen or what would we predict if we knew nothing about a customer, okay? And then finally, phi tells us that how much does a specific feature push us away from that baseline, all right? And that is applicable for each of those features there, okay? So how do we calculate this? Okay, that is all theoretical, but in practice, how do we calculate this, right? Well, the bad news is that this actual calculation is exponential, okay? Is actually 2 raised to the power m, where m is the number of features. So for 3 features, we'll have 8 combinations. How? Well, we could look at this example. So let's say that we have, again, a credit risk application or a system or an ML system. And we want to find out how much does each feature contribute for a loan application, okay? And we have age, income, and the credit score. The thing is that we have to try all combination of features. So first we try with no features, okay? Then each one of them, then a combination of those 2, and then all those 3 features. That's how we get our 8, okay? And it actually calculates all of this and just averages all of the combinations, and that's how you get for each feature, all right? Now, thankfully, we have some approximation methods which help us relieve our pain of this, okay, of this exponential calculation. So there are actually multiple of them, but I'm going to talk about 3 of them. The first one being the kernel SHAP, okay, which is applicable to any model type, okay? This is truly model agnostic, but it's really slow for large data sets. Then we have the tree SHAP, which is, as the name suggests, it is optimized for decision tree models. And when I say decision tree, I really mean any kind of decision tree. So I mean random forest, a simple decision tree, a boosted decision tree like XGBoost or like GBM, you name it, right? And the way it does that, it basically exploits the hierarchical structure of the tree, okay, which is its own structure, basically. All right? And then the last one is the deep SHAP, which is, as the name suggests, is for the deep neural networks. And the way it optimizes it is through leveraging backpropagation, okay? So for this case study, we're going to focus on the tree SHAP and the deep SHAP, okay? So enough of theory. Let's see how all of this plays out. The first one, the first case study we're going to talk about is the decision tree. Okay? And the data set that we're going to use is a banking problem. Okay? And we'll be using XGBoost for this task, and which is very popular for so many different tasks, maybe too popular in my opinion. But anyway, so the business problem here is that a Portuguese bank wants to predict which customers will subscribe to a term deposit based on direct marketing campaigns. Okay? So you can think of term deposit as just a certificate of deposit so that their money grows. That does not grow until inflation, but they seem happy about it. But anyway, but this is a very relevant problem because we in different kind of situations, we actually try to maximize revenue or conversions, right? And this data set, by the way, is like freely available through the UCI ML repository. So yeah, so it's very easily available there. So a little bit about the data set itself. It is a tabular data, which is like hence XGBoost. The features include some customer demographics, some financial details, some previous interaction history with the same customer, and what was the outcome behind that. So this is a binary classification problem. So we have two features, which is yes, meaning they did subscribe, and no, meaning no, they did not subscribe. Okay? The number of total samples is just over 45K, and we use an XGBoost classifier here. Okay? And again, the goal here was not to make the best model out of this possible, but actually to describe how explainability works. But nevertheless, though, I mean, we got a pretty decent AUC here, so which means that we can trust the model's predictions, fairly well, right here. So let's look at some of the code snippet that we use for the SHAP calculation. So it's pretty simple. We import the SHAP library, okay? XGB is our trained XGBoost classifier, okay? XTest is our test data set, or you could think of the production data set that you're getting. And then we set up like our explainer object. So like SHAP provides different explainer objects. So here we're using the tree explainer since we are using a decision tree model. So here we're using the tree explainer. We just pass it on with the XGB. We get the explainer object, and then we calculate our SHAP values on the X test. Okay. Now the SHAP values just returns the same shape as the X test. Okay, or the data that you provide. So here in this case, it's just over 9K and then 15 features in this case, right? But if you think about it, like SHAP values are just a matrix or a tensor. I mean, by itself, it's very difficult to interpret what's really going on underneath. So being able to visualize them is the key. That's how you know what is going on. And that's how you can convince some stakeholders that your model is doing what it's supposed to be doing. So let's look at some of the plots. The first one is I'm going to talk about is the global explanations and with the B-swarm plot. Okay, so this is how a B-swarm plot looks like. Okay, there's a lot of information thrown at you because you're actually looking at quite a few different dimensions here. Okay, and global explanations because you're looking at the whole data set as a whole. You're not looking at just one single instance. Okay, and that's what I mean by global. Now, this basically provides you with a high-level summary of the model's behavior, and it's very useful for understanding the impact of each feature out there. Okay, they're ordered by their mean absolute SHAP values in descending order, so you can say that they're ordered by their importance. You can tweak that, and then, by the way, each dot here is a data point in your data set. So you're actually showcasing all of the data points in this graph, okay? So a wide spread means that the feature impacts different customers differently, okay? So you can see a wide spread for the campaign feature, for the age feature, for the P-days feature, but then the tight clusters mean more consistent behavior. You can also see some features which are very tightly clustered there, okay? And yeah, as I said, they actually represent each feature's output on the model's predictions, okay? So SHAP values represent the impact of each feature has on the model predictions, okay? And the positive SHAP values indicate that the feature pushes the model prediction higher towards the yes class. So on the x-axis, you have the SHAP values, right? So a positive SHAP value indicates that the feature pushes the model prediction towards the yes class. Yes, in our case, is our subscribing to a term deposit, okay? And the negative value just is about the no class, which is that they are less likely to subscribe to the term deposit, okay? And the distance from the center indicates the magnitude, okay? By the way, the actual value of SHAP value doesn't really matter. What really matters is the relative values, okay? So if you see the feature, for example, campaign, it has a very negative SHAP value, okay? Compared to something, let's say education, which is clustered in the middle. It just says that the campaign feature is much more decisive in making the predictions move from one location to another, okay? And then one more interesting thing is that the ones that are grayed out are actually categorical variables, okay? Now, since categorical variables don't have any order, that's why they are actually grayed out. So if you look at this, you can actually gain some insights out of this. So let's look at the balance feature, okay? Customers with more balance in their account, balance basically means the amount of money they have in their accounts, are more likely to subscribe to a term deposit. You can see because it's on the red end, and red means high values, right? So it's on the positive SHAP value spectrum. Similarly, if you look at the campaign feature basically says that customers who have contacted more frequently in the current campaign are less likely to subscribe, okay? So that's pretty interesting here. So, but now we actually saw that the dependency plots or the categorical features are not really showcased well in the B-swarm plots, so that's why we have dependency plots. So it is for a deeper analysis for a single feature. So you're zooming into one single feature and its effect on the model predictions. And here we have 4 dependency plots. 4 of them are categorical variables. So now you can see that the SHAP value, like previously, it was on the x-axis. Now it's on the y-axis. So here, let's look at the top left. So homeowners, okay, if you're a homeowner, you're less likely to subscribe because you can see that most of the yes values are actually below. So the SHAP values are actually negative. Single and divorced customers, if you look on the bottom left, which is the SHAP dependence for the marital feature, is actually, so single and divorced customers are more likely to subscribe, okay? So that's pretty interesting as well. And if you look at the bottom right, if the previous marketing campaign was successful, then the chances increase dramatically of subscribing to the term deposit. You can see that all of the data points are actually positive. All right. Now, not all features are actually good separators. So you can see the education feature is not that great. Okay. So in this manner, we can make some informed decisions out there. So now let's move on to the second one, which is the neural networks. Now, I chose this because it's a completely different problem. So we talked about the binary classification. This is the multi-class. That was tabular data. This is the time series data. Okay, that were decision trees. This is a neural network. So we're looking at the human activity recognition data set. Okay, this is also freely available. And what you're basically looking at is like 30 volunteers between ages 19 and 48 wore smartphones on their waist and went about the daily activities, okay? The phone's accelerometer and the gyroscope captured every movement that they made, all right? And this isn't just academic, right? I mean, this technology actually powers any kind of fitness trackers, your Apple Watches, your rings, right? So like any kind of fall detection systems, you name it, right? And then you're trying to classify them into 6 different activities. You have walking, walking upstairs, walking downstairs, sitting, standing, and lying down. Okay? So now if our CNN can distinguish between walking upstairs versus downstairs using only sensor data, what exactly did it learn? That's what we're trying to figure out. Okay? So a little bit about the data set. It's a multivariate time series. There are more than 500 features. You have raw gyroscope readings and accelerometer readings, and you also have some engineered features as well in the frequency domain and the time domain, means, standard deviation, correlations, etc. You have 6 classes, and it's a multi-class classification. The model we're using is a 1D CNN using PyTorch because it's the time series data. And there are some pre-processing steps that we usually do, which is normalizing the data between 0 to 1 and convert this into a window of sequences. Okay? This is our CNN classifier. It's pretty straightforward. It's a 2-layer CNN with a tan activation. There is nothing fancy going on here. Again, the focus is for the explainability, not the best model performance. But talking about model performance, it's not that bad either. So for every for every class, we have an F1 score at least greater than 0.85. So we're doing pretty good, so we can trust the model outputs there. So let's look at the SHAP calculation here. So like here, it's pretty interesting. The first step that you do, like again, we import the SHAP library, but the first step that we do is create a background data set. This is very important, right? Because the background data set is the E of F, or the expectation that I mentioned before in the math, right? And ideally, we need to represent this with a production data set or a distribution, but only about 100 to 200 data points, okay? And all classes should be present. So here, what I'm doing is I'm just creating a balanced data set with at least all of those classes having like 20 data points, all right? Then I set up the deep explainer object because we are dealing with a neural network, and we are just calculating the Shapley values. Now here you can see that the shape is actually in a 4D, right? So the first one is the number of instances. In this case, I just took 1,000. And then you have 561, which is the number of features, 64 being the number of time steps, and then 6 being the number of classes. So we need to convert this 4D tensor to a 2D tensor in order to visualize our plots, okay? So what do? We actually extract the feature importances by taking an aggregation over the time steps, right? Now, there are multiple ways to do it. I just did it the most simplest way, which is taking the last time step, okay? You can actually average it out or do like some other combination there as well. And then you are just taking the plot for the walking class, okay? 0 means the walking class here. So now what happens is that in a multi-class setting, we have a set of SHAP values for every class in a one versus all fashion, okay? So in a binary class, we just had 1, right? But here you have to do it for all 6 classes. So here, this is, for example, a B-swarm plot for walking, okay? Now what's going on is, again, the same concept applies. The positive SHAP values pushes the feature towards the positive class, and the negative value reduces the model's prediction towards all the negative classes. But here, the key thing is all the other negative classes, not just one negative class, right? All the other in this case would be anything but walking, okay? Now, the thing is that if you look at this, now this is pretty interesting. If you just focus on the first feature here, okay? It basically says that the angle between the mean gyroscope signal and the mean gravity signal is smaller while it's walking, because you can see the blue values are on the right, okay? And if you look at the fourth feature right here, right, you can see that the low values of the gravitational acceleration along the x-axis pushes the prediction away from the walking class. Okay, so that's pretty interesting. And what's amazing is that our CNN discovered human biomechanics here. So it's actually doing that internally. So it learned that walking creates a specific signature in how our body moves with relation to gravity. Now you can see a sitting versus lying down, right? So, and I'm just gonna brush up on this, but you can see the first 3 features here. The first 3 features is pretty interesting, as the whole distribution is actually flipped. So it's actually the mirror image of each other when it's compared to sitting versus lying down, okay? Now, let's look at the dependency plots. I'm just going quick because I don't have much time. But in the dependency plot, you can just focus on the top feature here. Again, the pattern is flipped in walking upstairs versus standing, right? So now a pretty interesting thing is local explanations, okay? Now here you're zooming in into one single prediction right there, okay? So looking at the pattern, you can see that almost all the top contributors are actually gravity related, okay? And again, here the positive SHAP values push the prediction towards the lying down class, which is the class for which this local SHAP values are, right? And the negative SHAP values push the prediction away from the lying class here, okay? So some of the things to look out for and the limitations here is that SHAP explains the model, not the reality. So it tells you what the model learned, okay? If your model is biased or poorly trained, SHAP will give you a perfect explanation of that bias, okay? Not the truth. Now for large data sets, the calculation is very resource intensive, okay? And some of the bottlenecks are the background data set, the model complexity, the number of features, and the multi-class problems. The SHAP values can be misleading when features are very highly correlated. Like, for example, let's say age and years of experience. So what it does is that it just arbitrarily splits the credit between them. So you want to avoid that, right? Just be wary of that. And then, of course, correlation does not imply causation. And results depend on the choice of the background data set. Okay? With that, thank you. That was right on time.
So we have 5 minutes for questions. And first of one is, could you repeat how for one data point and one feature you determine the SHAP value from the trained model?
Okay, I think the user is talking about the local explanations. All right. So what's going on is that here you have a plot for this is for one data point and for one class. Okay. Now for one class, you can see the values that these data points have. So on the left, you can see like 3.4. That's actually the value that this data point has, right? And what this really means is that all of the features here, right, tend to push the prediction towards the lying down class. Okay, all of the red values here, which are positive, in net total, the whole thing is positive. Okay, there are some blue values, which basically means that those features, the value of those features, tend to be not lying down, but it is mostly positive, so that's why it is positive.
Next question is, if you apply one-hot encoding to categorical features, can I compare them back and have dependency plots?
Let me think. It is more complicated than you think. So what I usually do is that if it's a decision tree, and if I'm using an XGBoost and a light GBM model, I use the categorical feature that they have, which means I encode them the way they are. I don't do the one-hot encoding if that library supports. If you do that, that becomes much more easier to interpret. What happens is that if you do the categorical, let's say encoding, like the one-hot encoding, and then you have like 10 categories, which means you'll have at least nine columns, right? So those 9 columns can actually cloud your judgment and your top features right there. So it is possible, yes, but I would still like to use some kind of like an encoding, like a decision tree that you do, right? But for neural networks, of course, you have to do it. So it's fine.
Thank you. And next one is, what are assumptions, caveats, cautions, and critiques related to Shapley values?
Yeah, I think the biggest practical critique, I would say, is the correlation thing. So if the features are correlated, as I said, they would actually be, it might give different results for the same or similar data point. Okay, it will just split the contribution between those, arbitrarily split them between those correlated features. So what I do usually is I make sure that I find a correlation matrix and combine them into one single feature. So I could use a PCA for that. I could, sometimes I've also used an autoencoder for that if we are using autoencoder in the previous or the pre-processing steps. But you have to be really careful about that. Okay. And another thing is really the complexity of this whole calculation. You really have to be careful with the background data set as well. So if you choose the wrong background data set, then you're kind of messed up there. Yeah.
Okay, the last one is, I like the question. How does SHAP perform against sampling techniques like Sobol sampling to calculate and show the sensitivity of the model to features?
I'm not sure. That's a good question. I would like to know myself.
That's it, and thanks again for speaking.
Thank you.